In this tutorial, I am introducing immediate inferences on the square of opposition. So, just to review, an immediate inference is an inference that goes directly from one categorical proposition to another categorical proposition. So, for instance, a categorical proposition like all S is P makes a claim about the relationship between S and P, and by knowing that claim and assuming or presupposing the truth of that claim, we can infer the truth or falseness of some other categorical proposition that corresponds. So let's first talk about what corresponding propositions are. Corresponding propositions are categorical propositions that use the same subject and predicate terms, not necessarily in the same order, but every categorical proposition has got a subject term and a predicate term. So if you think about those two terms as the categories that are involved in a categorical proposition, a corresponding proposition is going to involve those two terms. So let's take an example. All S is P corresponds to some S is not P. Why is that? They're corresponding propositions because they use the same subject and predicate term. So, for instance, to take a particular model, a model is when we substitute real categories for the variables S and P. So here's a model. All cows are mammals. Some cow is not a mammal. Those are corresponding propositions. Now, you probably, if you think about cows and mammals, you probably notice that if all cows are mammals is true, then some cow is not a mammal cannot be true. And that's exactly right. That is one of the immediate inferences on the square of opposition. It goes across the diagonal. And what we'll see is that these diagonal relationships work in a similar way. And for that reason, we call them by the same name. They're called contradictories. So, contradictories. How do contradictories behave? Well, we can work this out by using models like if all cows are mammals is true, then it cannot be true to claim that at least one cow is not a mammal, because we've just said that they all are. So one way is to do it sort of intuitively by using models, and those models tell us, in terms of the patterns, they tell us, they give us some insight into these relations. But a more exhaustive or definitive way is by looking at the relationship as it's depicted by the Venn diagram. So have a look at all S is P. In the diagram, we have shading, which means that that region of S is empty. And if that region is empty, then it can't possibly be the case that there's an X in it. So in other words, if this diagram represents something that is asserted to be true, then this diagram says something that directly contradicts something about this assertion in the diagram, right? Now, technically, diagrams don't assert anything. They just represent assertions. So what we can say more formally is the diagram that represents all S is P is inconsistent with the diagram that represents some S is not P. And the particular inconsistency has to do with the fact that the O proposition requires an X where there's shading in the proposition that we are assuming or presupposing as true. And it turns out that's what contradiction is all about. Contradictory propositions always have opposite truth values. So let's take another example. Look at no S is P. If no S is P is presupposed to be true, then this diagram depicts the relationship between S and P. And if you go across this diagonal to the corresponding I proposition, you'll notice that the I proposition requires there to be an X exactly where the E proposition has shading. In other words, there's an X where the E diagram says that you have to be empty. So if no S is P is true, the corresponding I proposition is false. So, in other words, they have opposite truth values. So let's see how that works from the other direction. Suppose the O proposition is true. So we're going to suppose that O is true. If O is true, then this diagram represents the relationship between S and P, and it says that there is at least one thing in the S circle that's outside of P. So if this diagram represents a true assertion, then look at this diagram for the A. The diagram there says that it wants to have shading in the region where the O proposition asserts that there's at least one X. So obviously, if we take this O as true, the corresponding A has to be false, because you can't have shading there. Why? Because that region of S is not empty by the assertion that we made that the O is true. Similarly, if I is true, then this relationship holds between S and P. And if this relationship holds, then the assertion by the E that there needs to be shading in this overlapping region between S and P cannot be true. So again, what we have found is that if we start with any one of these being true, across the diagonal, the corresponding proposition has to be false. And this relation is always across the diagonal, right? Now, as an experiment, let's see what happens if we say that one of the propositions is false. So let's take as our starting point this A, and we'll say that the A is false. Now ask yourself this question. If A is false, what is it that would make this assertion false? Well, if you think about it, the A is claiming that all S are P, and what would make it false to say all S are P is if we could say that some S is not a P. In other words, the A proposition asserts this shading to make all S P, and if that's false, then it means that there has to be something where that shading is that makes that proposition false. So again, no matter whether we start with true or false, if we cross the diagonal with the relation of contradictory, we're going to get opposite truth values. Okay, so that's the first. That is the first of the relations. I'm getting rid of some of these extraneous marks so that we can examine a different relation. Okay, so what about the relation between all S is P and no S is P? Let's consider this, okay? If all S is P is true, then could it be true to say that no S is P? Well, if you think about it, you'll realize that there's some inconsistencies. If all S is P is true, then there's shading here in the region of S outside of P, and there's also an X in the region overlapping S and P. If you compare that with the diagram for E, there's the A requires shading where the E has an X, and the A has an X where the E requires shading. So what that means is that if all S is P is true, the corresponding E, no S is P, cannot be true. All right? Okay, so far so good. Now, what if the E is true? What if E is true? So let's put a true with a little circle to indicate that we're examining that possibility, right? So if the E is true, then the relation depicted in the diagram obtains, and if it does, then we have inconsistencies with the diagram here for the A, right? In other words, there's an X in a region for the E that the A proposition claims has to be empty, and there's shading in the E diagram where the A proposition claims there has to be an X. So what it looks like in this case, because of the diagram, is if E is true, the corresponding A has to be false. Okay? Now, let me ask you this. Is it possible for both of these to be true? Well, we've just proved that it is not possible, because if A is true, the corresponding E has to be false. And if E is true, the corresponding A has to be false. So we've settled that question. But what about this question? Could they both be false? Well, here's the interesting thing. If they were both false, then there's something that makes this A false, and there's something that makes this E false. But the interesting thing about that is what would make this A false is if there's an X where the shading is, and that's exactly what we have with the E, if that were true. But over here, if the E were false, then there has to be an X where the shading is, and that's exactly what we have over here with the A. So when we ask the question, can they both be false at the same time? The answer is yes, they could both be false. In fact, if they were both false, then all we're really saying is simply that some S's are P's and some S's are not P's. That's exactly what would make both of these false. So let's think about that. If some S's are P's, then that makes it false to say no S is P, because that's where the shading is. And if some S is not P, then it makes it false to say that all S is P, because that's where the shading is for the A proposition. So this relation, which incidentally is called contraries, cannot both be true, but they could be anything else. So in other words, they cannot both be true, which means that one could be true and the other false, the other true and the one false, or both false. So what we say about contraries is contraries cannot both be true. Now, down here across the bottom, you might suspect that we have a similar kind of oddity. And in fact, we do. We call this subcontraries because the relationship is slightly different for subcontraries. So what we've just proved is that contraries cannot both be true, and subcontraries are the exact opposite of that. They cannot both be false. Okay, so let's think about this. What would make some S as P false? It's if we had shading in the region of S and P overlapping. In other words, just like we have here with the E. What would make some S is not P false? What would make that false is if we had shading here. Now think about it. If this is false and this is false, then the corresponding A and E both have to be true, because that's where we need shading to make those particular propositions false. But we just proved that contraries cannot both be true. So contraries cannot both be true, and subcontraries cannot both be false. So how does that work practically speaking? Well, if you knew, for instance, that some S is not P is false, so we can assign false to that, then what do you know about the corresponding I? Well, because subcontraries cannot both be false, the corresponding I would have to be true. So that's an immediate inference that we can draw based on the relationship subcontraries. Okay, excellent. Now, a couple more. What if we knew that all S is P is true? If all S is P is true, then on the Aristotelian interpretation, which includes the existence of the universals, we would also know that some S is P would have to be true. This relation is called subimplication. Subimplication says that if the A is true, the corresponding I has to be true. And if the E proposition is true, then the corresponding O has to be true. Okay, so it goes down from true to true. So I'm circling the starting point to let you know. So if we start with a universal true, then we can go down the square of opposition to the corresponding particular, and it will be true. But does it work in reverse? In other words, suppose some S is P is true. Does it follow that all S is P must be true? No, it doesn't follow, because the fact that some S is P is true doesn't guarantee that they all have to be, right? Same thing over here for some S is not P. If some S is not P is true, it doesn't follow that no S is P has to be true. It might be true, but then again, it might not. And the whole point of an inference is, if we know the truth value of one of them, we can infer, like 100% certainty, we can infer the truth value of the other one, right? So let's ask the obvious question then, is if the I is false, in other words, we're starting down here with a false, do we go up and get a particular truth value? So let's think about this, okay? Look, if some S is P is false, then what would make it false? What would make it false is having shading where the X is. In other words, the E being true would have to be what makes the I false, right? But if the I is false, then what it means is that it's not the case that some S is P. And if it's not the case that some S is P, then it can't possibly be the case that all S is P. So if it's not the case that some S is P, then it means that no S is P. And if no S is P, it can't be true that all S is P. So it turns out that going up from particular to universal works if you start false and the inference goes to false, right? This relation is called super implication. So superimplication goes up from the particular to the corresponding universal, and it goes from false to false. Same over here. Let's look at the reasoning here. So if it's false that some S is not P, why would it be false that some S is not P? It would only be false that some S is not P if all S is P. So if all S is P is true, the corresponding E, no S is P, must be false. So that gives us our inferences on the square of opposition. These inferences are contradictories across the diagonals, contraries across the top, that's for universals. What about universals? Universals cannot both be true. Subcontraries across the particulars, subcontraries cannot both be false. And now we have subimplication and superimplication. Subimplication starts with the universal on the Aristotelian interpretation, in other words, with the existence built in, the X's. It goes from the truth of a universal down to the truth of a particular, and it works for both affirmative and negative propositions, right? And then we also have superimplication, which goes up, but it goes up from the false particular proposition to the false universal. Those are the inferences on the square of opposition.